Please, Sarah, thanks both.
Thank you. Thanks, Liz. Thank you guys for coming. All right, since I have you as a captive audience, I'm going to start and tell you a little bit about something that's near and dear to my heart. This program, which is absolutely phenomenal. And then I'll get to some math and talk about complex dynamics, dynamical data from topology to algebra. But first I have to open with a story that involves this. So I was here, gosh, it's hard to remember pre-pandemic, but it was 2017 or 2018, and I was speaking in the Young Mathematicians Conference. And it was an excellent experience. I met a lot of really cool young people, and I was giving a talk called The Mating Habits of Polynomials, something in complex dynamics that's really cool. I was walking around outside and admiring your beautiful campus, and I walked by the math building, and there it said mathematics. And then I thought, why is there a sign falling down? They should really replace it if it needs all those pieces of tape, because it needs to be repaired, obviously. And then I looked at it more closely, and of course, there are these red X's only over the M's. And then I realized exactly why it was there. So we at Michigan, we don't sort of return that kind of thing. I've never noticed the O, the S, and the U that are X'd out on our signs, but maybe I'm just not looking hard enough. All right, so I'm going to tell you a little bit about the Math Corps, which I'm involved with. I'm the director of a Math Corps site at the University of Michigan. I found out about the Math Corps kind of by accident a couple years ago. It's an amazing program for middle school kids and high school mentors, and it started 30 years ago at Wayne State University in Detroit. So after I learned about it, I thought, oh my gosh, why don't we have one in Ann Arbor? So we started one in 2019. And this is for middle school kids from Ypsilanti, Michigan, and high school mentors from that same area. So the Math Corps is phenomenal. 90% of the kids who grow up in the Math Corps at Wayne State in Detroit will graduate from high school, and among those, 90% will go to college. So that's pretty great. And so I just wanted to share a little clip with you guys about what the Math Corps is, and then we'll get to some mathematics. So one reason I'm doing this is not only to tell you about how awesome this program is, but also because I don't have a stable funding situation for it yet. So if any of you know anybody with really deep pockets who want to make the world a better place, please let me know. I'll happily share all of this with them. So this is just a short clip that will tell you exactly, or maybe give you a better idea of what this is. And I hope you can hear it.
All of our students are unique, and that means that they're special. So we have to build our kids. We have to give them the values that we think are important in life, teach them kindness and integrity. You teach them things here too. So mathematical thinking, this is the Math Corps. That's not meaningless. It's certainly not primary. Primary is building lives, not building mathematicians. But this is a place where you learn to think. And so this idea of loving and believing in kids is something that we define. Here's what love means. Here's what believing in kids means. And it becomes real. Then you live it every day.
But essentially, the high school guys carry the program. Most of them have been with us for years. They understand the culture. They understand what's going on. And so they are the bearers of the culture. And the beauty is, the little guys come in and they form these relationships with the high school guys because they look at them as big brothers and sisters. And conversely, the high school guys always speak to them as my kid. From Math Corps, we'll have leaders and just kind of the ripple effect of kids realizing their own greatness and the joy of giving back in kindness.
The Math Corps became all about that. It became a program about kids caring about kids.
I should say I visited and I saw the kids dancing in their chairs, and they were all going like this, and they were going like this, and I was really confused. They used hand signals there. And this is the signal. It's American Sign Language for applause. So they use it for praise or agreement. And this is the support signal that they use when the kids get up to the board and have the courage to do a problem in front of their peers. Anyway, it's a phenomenal program. It's very exportable. You know, anybody who could use a Math Corps site in their area, geographic area. Okay, so let's get down to business. All right, this is going to be a talk in complex dynamics. That's my research area. So in complex dynamics, we like to think about holomorphic functions usually on complex spaces, and we think about them from the point of view of iteration. So the domain and codomain of my functions are going to be the same. And I want to think about iterating these functions, and I want to study what happens. Okay, Okay, so that's sort of basically what complex dynamics does. Almost every talk in complex dynamics begins with a discussion of the quadratic polynomial family. So I'm going to be thinking of these quadratic polynomials as functions mapping the complex plane to itself. And I want to think of a whole family of these polynomials, not just one in isolation. So given a complex number c, I get a complex of quadratic polynomials e squared plus c. And for every c value, I can study this particular polynomial as a transformation from c to itself. And you might ask, well, that's kind of strange. A complex polynomial seems to depend on maybe more complex numbers than just the constant term. I can write an arbitrary polynomial like this, where there are in fact 3 coefficients. So why am I getting away with something of this form? And it turns out that when you study dynamics, you're allowed to pick a normal form you can conjugate by an automorphism of your ambient space. The automorphisms of the complex plane are exactly the affine transformations. So I can conjugate any polynomial of this form to, in fact, a unique polynomial of this form. And I'm not losing any information. And actually, this helps me out because if I were to study the space consisting of all of these guys, that's 3-dimensional. And I have a hard time drawing that. 3 complex dimensional, so it's sort of even worse. And here, this is just 1 complex dimensional. This is just a copy of C parameterized by where this lives. So that's why I'm allowed to restrict my attention to maps of this form. So a very natural object to study associated to iterating these polynomials is this set case of C. It's called the filled Julia set. And by definition, it consists of all points in the plane so that when you look at the orbit, this sequence is the orbit of that point under the polynomial piece of C, that orbit is bounded. So what is this really saying? You take a point in the complex plane, you plug it into z squared plus c, you take that output, and then you plug that into z squared plus c, and then you take that output, and you plug that into z squared plus c, and you keep going. So for every starting point, you get a sequence of complex numbers. That starting point is in your filled Julia set by definition, if and only if that orbit is bounded. What do I know about that set? That set is non-empty always, and it's compact. So let's look at some examples of the kinds of shapes that one can obtain this way. This is a good place to start. So if we set c equal to 0, we're left with a polynomial z mapped to z squared, the squaring function. You can work out by pencil and paper, just like Fatou and Julia did 100 years ago, what the filled Julia set is for the squaring map. It's a set of all points with bounded forward orbits under squaring. That is exactly the closed unit disk. It's in black. And its complement, which is green, those are all the points such that if you started there, the associated orbit would shoot off to infinity. Okay. And you can see an orbit highlighted in white. This is the starting point. This is the next point, next one, the next one, the next one, and so on. And you can see why this orbit is not only bounded, but it in fact will converge to 0 under iteration. 0 is an attracting fixed point of the squaring. All right, let's look at some more exciting examples. When c is -1, we have the polynomial z maps to z squared minus 1, and we get this guy. So in black, you see the filled Julia set. You'll notice some symmetry in this example. The real axis skewers this picture like this. So this map is symmetric with respect to reflection or complex conjugation. And the reason for that is that it has real coefficients. You'll also notice that it has some symmetry with respect to reflection across the imaginary axis, which is right here. 0 is in the center. Why does it have that symmetry? Well, if you look at the form of our polynomial, the map is even. Z and negative z have the same image. Okay, which means that you have symmetry with respect to reflection through the origins in the complex plane. Right? Z and negative z have the same image. So there's some symmetry with respect to reflection through the origin. So we have symmetry this way, symmetry through the origin. So we will also get symmetry this way. Okay. So here the orbit of a point is highlighted. You can see that that orbit is going to converge. It doesn't converge to a fixed point. It converges to, this is a 2 cycle, cycle period 2 that's attracting. This guy, z squared plus I, this looks a little bit different. The Phil Julius set is black. You might say, what? It's very thin in this picture. This is a dendrite. That Phil Julius set has empty interior. It is connected, this set. Okay. It has no attracting cycle other than, if I think of it on the Riemann sphere that is adding the point at infinity to the plane, I can think of infinity as an attracting fixed point for all of these maps. Yeah, we can think of the points that are attracted to infinity as the green points in the pictures. So this has no attracting cycle in the complex. And there's this guy, z squared minus 2.5, which you'll notice is not connected. In fact, this is a Cantor set. Okay. So just in this beautiful array, this gallery of 4 examples, you can see that there's a bunch of different kinds of shapes that we can get for the Phil Julius. So you can ask, well, how do we study how these shapes change as you vary that C? That's one question we could ask. I want to point out something also. There's a special point in each of these pictures. Each of these pictures has a distinguished point in the plane. It's a point of symmetry, and it is the unique critical point of the polynomial z maps to z squared plus c. A quadratic polynomial will fold over the critical point. I'll study that if you look at real quadratics. Those are just parabolas, and they fold. So these quadratic polynomials are transforming the plane by folding over the critical point. So there's necessarily symmetry with respect to that critical point. And in our coordinates, that point's at 0. So you can see it geometrically. You can also see it in our coordinates. It's here, it's there, and it's here. That critical point is going to play a very important role in what we're going to talk about next. Okay. So one thing you can do just by looking at different examples is try to understand special subsets in parameter space, that is in the C plane where the parameter C comes from. We know that there are some C values for which the Phil Julius set is connected, and there are some C values for which it's not. So that just motivates a definition. What are the C values for which it's connected? I'll suggestively call that, oh, I should have used the Michigan M. I'll do it next time. I'll suggestively call it script M, the set of all C for which the Phil Julius set is connected. Okay, we want to understand that object. What does it look like? And how would we even begin to try to understand it? So that's one thing we could study, but we also saw some other things that we could look at. We saw that there's some C values for which the polynomial z squared plus c has an attracting periodic cycle like this one with dynamics. And we saw some C values for which z squared plus c doesn't have an attracting cycle in the plane like this one. So we could try to study the set of all parameters H. Set of all parameters for which that polynomial z squared plus c has an attracting cycle. There's 2 subsets in the C plane that we can try to understand. And these sets have been studied extensively for 40+ years. Okay. Now, if you had this definition on the paper in front of you or on the slide in front of you, somebody said, draw me a picture of this, please. What would you do? Kind of hard to, okay, well, we can compute a bunch of examples and use the computer to draw the Phil Julius set, but then how do I get a certificate that a subset of the plane is connected or not? I don't know how to do that. So how do you even know where to start? Similarly here, I can do some examples, but how do I get the computer to tell me, yes, this polynomial has an attracting cycle? Okay, well, maybe I can do some calculations and I can compute all the periodic cycles up to period like 5. They're going to be a lot. But maybe there's an attracting cycle of period 61. My computer just won't be able to find. How do I know? Well, Fatu and Julia did the heavy lifting for us, and there's a theorem that says that you can understand these sets using the critical point and its forward orbit. And that is extremely useful in complex dynamics just as a whole. If you have a function, you want to understand it from the point of view of iteration, like polynomial z squared plus c, or more generally, what you should do is write down all the critical points and figure out where they go under iteration. And I'm going to illustrate the power of that idea by changing these definitions or giving you alternative definitions. And those alternative definitions are going to get us a foot in the door for drawing pictures of these objects. So this set, the connectedness locus, is actually equivalent to the subset of the C-plane for which the critical point has bounded under z squared plus c. That's huge, because what it means is I now have a chance of understanding what this is. All I have to do, I take a candidate parameter c, and then I just have to figure out what happens to 0 under iteration. Does that orbit escape? Yes or no? If it doesn't, then by this theorem, the Phil-Julia set's connected. If it does, the Phil-Julia set's disconnected. So that's a big deal. And similarly here, this is an alternative definition. Turns out if the polynomial z squared plus c has an attracting cycle, it necessarily attracts a critical point. Since I have only one critical point to spare, it will have to attract this one. So again, we just follow around the orbit of 0 and see what it does. From these definitions, this blue and this pink definition, you can already see, we've already gained some mileage, there's a relationship between this set and that set. There's a containment relation, right? If 0 is attracted to an attracting cycle, then it has bounding. So in fact, having an attracting cycle turns out to be an open condition. So it's not only that H is a subset of M, it's a subset of the interior. And I should say, let's go back. This example, this was I, z squared plus I. This is an example of a parameter c equals I that belongs to M, but not to H. So that means that M is not equal to H. Okay. It's bigger. Okay. All right. So you might have seen where this was going. The set script M is called the Mandelbrot set. And there it is. It's this black blob over here, just so you can get your bearings. Not quite this tall. Does anyone have a pencil or the chalk is going to be too short? I just need to point at the here. I can probably, I don't know, paint it. I think this will do just fine. Okay, the real axis skewers this picture right here. So this picture is symmetric with respect to complex conjugation. Why? Remember its definition. How is the Phil-Julia set for z squared plus c, where c is taken from right here, related to the Phil-Julia set of z squared plus c bar? You just take the picture and pull it. So this one's connected if and only if this one is, which is why it's symmetric with respect to complex conjugation. Okay, -2 is the tip of the tail right here. 1/4 is that cusp right there. I, remember z squared plus I, that skinny one, I definitely won't be able to reach, but 0 is here, and I is going to be on the boundary of this. It's on one of those antennas up there. I guess I could, oh, you know what I should tell you, it's like right around here and just flip it up. -I is right around there. Okay. So this is our Mandelbrot set. What do we know about it? It's compact, it's not empty, c equals 0 is in there, for example. And it's a theorem of John Hubbard, my thesis advisor, and his thesis advisor, and for N2ID, that this set is connected, which I think is beautiful. Because remember, it's defined as the connectedness locus of the family z squared plus c, and it also has that property. Okay. There are some hard problems that are still open related to this. It's not known if the set is locally connected. I don't recommend, if you're a graduate student, that's not a good thesis topic. It's people have been trying to sort that out for years. And in fact, a motivation for why they even asked that question is related to the question of whether these are equal. Remember, this is a subset of the interior. It's not known if it's equal to the interior. So this is called the density of hyperbolicity conjecture. It's wide open, and it turns out that that will be true if the Mandelbrot set is locally connected. So that's why people started asking the question, is it locally connected? If you zoom into the Mandelbrot set, there's like a 10-hour zoom on YouTube. Really deep in. You'll find tiny copies of it, and it gets very beautiful and wild and has all these tendrils. So it might look pretty locally connected, but it has a lot of really intricate structure way deep down. Okay, what are these integers? Well, each of these components of the interior that you can see is part of script H. Remember, script H, those are the C values for which there's an attracting cycle. And remember, if there is an attracting cycle, it has to attract our unique critical point. So what you can do is if you take a parameter from this main heart-shaped region, you'll have an attracting cycle period 1 that is a fixed point for P sub C. So we can label this whole connected component of the interior with the integer 1, because any C value from that component, the polynomial Z squared plus C, will have an attracting fixed point. And you can move over here and take a C value, you'll have an attracting cycle period 2. Any parameter taken from this connected component of the interior, P sub C, will have an attracting cycle period 2. So you can label all these connected components of the interior, well, the connected components of script H, with a positive integer corresponding to the period of the cycle. And you can ask, well, what happens to these integers? What do they look like as you move around geographically in this picture? Okay, so I hope I've convinced you that following around the critical point is kind of important. What the critical point does under iteration, kind of a big deal. So that kind of motivates studying this object. This is called the post-critical set, and it's just the union of the forward orbits. Sorry, the union of the points in the orbit of the critical point. Starting at the critical value does not contain the critical point itself unless the critical point happens to be in its forward image. Okay. So it's just looking at that sequence. All right. And we're going to restrict our attention for a second, well, maybe for the rest of the talk, to polynomials and more generally rational functions that have the property that that set is finite. So we know that the critical orbit is important. It's important for the topology of our Phil-Julia set. It's important for whether or not there's an attracting cycle. Let's insist that the forward orbit of our critical point is finite. See what happens. What kinds of maps have that property? Those are called post-critically finite. We've seen two examples already. This one and this one. What does the orbit of the critical point look like for those guys? For this map, I'm going to indicate the orbit of the critical point with this graph. There's a 2 over this arrow because 0, the critical point, maps forward to the critical value with local degree 2. This critical value, when you plug it in here, goes back to 0. I'm not going to put a little 1 here because my picture would be too crowded. Okay, but this is recording the local degrees, and imagine there's a 1 there, of how things map around. The finite graph, because the map's post-critically finite. This guy over here, 0, maps forward to the critical value I, local degree 2. That maps here, and that maps back. So this is another example of a post-critically finite polynomial. The critical orbit is finite. In this example, this point, this point, this point, and the point at infinity are all in the post-critical set. In this example, these 2 points and the point at infinity, which is ramified and fixed, critical and fixed for a polynomial, those are in the post-critical. So we have 2 examples of these special objects. Okay, the first thing I want to say about where these polynomials live in this picture, -1 is here, and we already talked about where I was. Please notice that if we have a C value for which Z squared plus C is post-critically finite, then it has to live in the Mandelbrot set. Right? Because the orbit of the critical point is finite, so it's bounded. So all of them live here. And the question is, are they special from the point of view of this set? And the answer is absolutely yes. There are these pristine little gems that are hiding in this picture. So let's find them. How do you find them? We're going to put a constraint, this is called a portrait. We're going to put this graph or this portrait constraint on this polynomial and try to find some more examples. So let's suppose we're interested in all c values for which 0 is in a cycle of period 3. Well, we know that 0 maps to c in that formula, and c is going to map to c squared plus c in that formula. And then we just insist that c squared plus c maps back to 0 when we plug it in. And that's going to impose a polynomial constraint on c. We're going to insist that the image of c squared plus c is 0. That tells me this. Okay, so the roots of this polynomial are going to be exactly those c values for which 0 under p sub c has that dynamics. That's false. There's an extra root. We ignore this one. This is a degenerate solution that corresponds to c equals 0. I don't want that one. So in fact, there are 3 places in the Mandelbrot set, 3 parameters for which the polynomial z squared plus c has 0 in the 3 cycle. Where are they? These 2 are here and here. These are complex conjugates. I've drawn the Phil-Julia set for each one. 0, the center of symmetry, is in a cycle of period 3. Here, complex conjugate, you get the conjugate picture, the conjugate cycle, and there's a real root here. These are affectionately known as the rabbit, the co-rabbit, and the airplane. So this is a rabbit because it has 2 ears. This is a co-rabbit because it is the co of the rabbit. And this is an airplane named by John Miller because it looks like an airplane flying. And I just erased, for some reason, this comment got erased. So let's highlight that. I looked around for a really good rabbit, one that had the right kind of angle and the airplane was hard to find too, just the right. So I want to study this from sort of an algebraic point of view. The roots of this are algebraic integers. This is a monic polynomial with integer coefficients. They're sort of even better. They're algebraic units in the ring of algebraic integers. And if you take one of them, you get your z squared plus c. And if you look at the post-critical set, remember that's the orbit of 0. So c, we just said, is an algebraic integer. C squared plus c is also an algebraic integer. So the whole post-critical set is a collection of algebraic integers. So what this tells me, that there's something sort of algebraic about this thing, these points, something sort of special. Okay. Okay. Right. So we said that the post-critically finite parameters have to live in here. In fact, in this family, they'll all be algebraic integers, and there'll be a countable collection of them. They're algebraic, of course, and there are infinitely many of them. And if you just decided to plot a bunch, you would get the Mandelbrot set in space picture. So the way that you generate this is you just compute all the examples for which 0 is in a periodic cycle of period n. You just generalize that exercise that we did before, and you take n to be larger and larger and larger, you'll get more and more and more and more algebraic integers. And one cool thing about this is that that very nice algebraic subset, it knows about the Mandelbrot set in the sense that you take the closure, in the analytic topology, it will contain the boundary, the Mandelbrot set. And the boundary, remember, is not something we understand. We don't know if the set is locally connected. But somehow these special polynomials know about this fractal where they live. So I kind of want to study them because they're so special from sort of 2 different points of view. And one is kind of more combinatorial. And it's a question about these kinds of objects here. And another one is about their post-critical sets. Sort of what do they look like? So let's start with this question. Portraits. Which portraits arise for post-critically finite quadratic polynomials? We saw that if we started with this portrait, this combinatorial constraint, we found 3 quadratic polynomials that realize this portrait. So that one's realizable. Is this one realizable? I start with a graph. There are weights on the edges for the critical points. And then I want to know, are there any polynomials, say of the form z squared plus c, that have that as their portrait? And the answer is yes, this one does. Okay, great. This is the unique one, in fact, of the form z squared plus c that has that as its portrait. And you might make a guess that, in fact, for quadratic polynomials, every possible portrait arises on this. So what has to be true about our portraits? Well, they're for quadratic polynomials, so there should be a fixed critical point mapping forward with local degree 2 corresponding to infinity. It has to be part of that. And then the other critical point has to have finite forward orbit. So there's one other point that maps forward with local degree 2, and it is either in a periodic cycle or it's eventually in a periodic cycle. So those are the 2 possible different kinds of portraits. Almost all of them arise, except for one of them. Does anybody know which one doesn't? There's exactly one of these graphs for which the solution set is empty. Oh, we know it's not this one. And when I tell you the answer, you're going to think I'm cheating, but it's for this guy. So this can be as long as you want. This is the problem. So does anybody see why this is bad? If I had a polynomial that had this dynamics, that means at this point, polynomials of degree 2. So every point has exactly 2 inverse images counted with multiplicity. This point has 2 inverse images coming from here, but it also has another one coming from here. So that's not allowed. But every other portrait is realizable, and I can tell you how a proof of that statement goes if you're interested. So all of them are realizable except for this one that's kind of cheating. And I would say that we shouldn't even have asked about this because it violates local degree restrictions. So that's not really a fair question. So a more interesting question is, if you have a portrait that has the right number of critical points, a fancy way of saying that is it satisfies the Riemann-Hurwitz, and it satisfies local degree constraints, meaning no point has too many inverse images, is that realizable? That's a better question. So in the quadratic case, we know the answer. Another thing you could ask, so that's sort of a combinatorial question about post-critically finite maps or quadratic polynomials. Another thing you could ask is, what subsets of the plane arise as post-critical sets? Remember, we were talking about algebraic integers before. So my graduate student, Jasmine Powell, decided to do an experiment. We were inspired by a beautiful picture that Bill Thurston sent me, gosh, in 2011, that he drew on a bus that's hanging in my office that Dan knows about. It's related to teapots. So here's one thing you could do. You can try to find all the post-critical sets, compute all this data for as many of these as you can. These will all be collections, finite collections of algebraic integers, and you plot them all in the same copy of the complex plane, and you get this. Kurt McMullen named this the Mandel fungus. And you can take the closure of this set, and you can ask questions like, is it connected? I have no idea. But it's pretty cool, and it's shaded according to density, which is also kind of cool. So you can ask a question, what subsets occur as post-critical sets? Here's sort of all the data at once, and what shapes combinatorially occur for these guys. I'll tell you what I know about that question. Okay, But what I want to do is sort of think more generally, because I know how to answer one of these.
Can you go back to that? To the fungus?
Yes.
So on the right, you seem to have, there seem to be two holes, but on the left, they're not two holes.
I sort of see two holes over here.
Okay, but so it's supposed to be symmetric?
It should be symmetric.
Okay.
That's what I'm expecting, yes.
All right.
Should have some symmetries. In
Okay.
fact, I think,
There's also
like a hole here.
no, there's this picture.
I know why that's
Right, yeah.
there. I know why that's there. That's true. I know why that's there. So I'll point out that this contains the boundary of the Mandelbrot set. Because it contains all the C values of all the post-critically finite guys, and this, the Mandelbrot set lives in the C plane. And remember, we saw in the Mandelbrot set in space picture that if you take the closure of those points, you'll get the boundary of the Mandelbrot set. So the Mandelbrot set is in here, and that's a good point. It is not symmetric with respect to reflection this way. But maybe what happens is all of this is just gonna fill it. But I have no idea. I think maybe this is what you get if you plot all the Phil Julia sets on top of each other. I'm not sure. It's kind of a fun, but yes, it looks, I think some of these shadings are artifacts of the way that the data is. Okay. So more generally, we just talked about quadratic polynomials, which is a good place to start. But in complex dynamics, one studies rational functions on the Riemann sphere. That's what P1 represents on this slide. So we can think of a rational map. We don't have to stick to polynomials, and we can ask these questions sort of more generally. And one thing I learned from Bill Thurston was, it might sound like we're maybe muddying the waters by thinking of this more general question. Why don't you just stick to quadratic polynomials, because those are easier than all the maps at once. But if you ask a more general or a broader question, it might be easier to see some structure in the answer you're getting. And it might be easier to say something about all of these questions instead of restricting to a special subject. So in fact, I can answer some of these questions related to this more general setting, and I will tell you about that right now. So a rational map on the Riemann sphere, you want to think in coordinates. It's just the ratio of two polynomials, P of Z over Q of Z, and a rational map of degree D means that these guys have degree D. At least one of them has degree D, and the other one could be degree D or less. Okay, you want to think sort of intrinsically, it's just a holomorphic map on the Riemann sphere of degree D. Every point, every generic point has D inverse images. Every point has D inverse images counted with multiplicity. All right. So once we have one of those objects, again, thinking of the domain and codomain as the same, we're going to define the post-critical set, the union of the forward orbits of the critical points. How many critical points are we entitled to? 2D minus 2. You can compute that with calculus by counting degrees of the equations you're getting, or this is really Riemann-Hurwitz. It's from the topological properties of a degree D map from a sphere to a sphere. Okay. So that's going to be important. Remember, critical points are huge for us. So 2D minus 2. Okay, so which portraits arise for post-critically finite rational functions? We've seen lots of examples of post-critically finite quadratic polynomials. What can we say more generally? Like,
What's the portrait?
it's this object here. It's
Okay.
this directed graph that's supposed to record the orbits of our critical points. So if I give you this graph here, and I say, is there a rational function of whatever degree that realizes this portrait, yes or no? Well, how would we set that up? So you take the combinatorial object and try to figure out what would have to be true about such a rational function if it existed. The first thing I'll notice is let's count critical points. So there's one here that maps forward with local degree 3, maps forward with local degree 2, local degree 8, 2, 2, and local degree 7. In the Riemann-Hurwitz calculation, how do you count critical points? This critical point counts as one simple critical point because it has minimal local degree as a critical point. 2. There's one critical point here, one here. This one is a repeated critical point. It counts for 7. Take the local degree and you subtract 1. That's its multiplicity as a critical. So if we count up, we get 2 plus 1 is 3, plus 7 is 10, plus 6 is 16, 17, 18. So this number for that portrait, 2D minus 2 is 18, which means D has to be 10. So if I want to find a rational function that does this, it has to have degree 10. So that's where I start. And I write down a general form of a rational function of degree 10. I use the coefficients as parameters, just like for z squared plus c. I want to make my life easier, so I probably choose coordinates and maybe set this equal to 0, this to infinity, this to 1. That's going to trim these down a little bit. And then I write down equations that come from this combinatorics in these A variables and B variables, and then I solve. Cross my fingers and I hope I have a non-empty solution. I have no idea if that one's realized. I didn't do the calculus. As you might imagine, these equations that you're going to start to get kind of unwieldy. But that's what this question is asking. Okay, I can tell you that in the non-polynomial case, not every portrait arises. This portrait does not arise. It's not realizable by a rational function. How do I know that? Well, let's just do it. It would have 2 simple critical points. So that means 2D minus 2 is 2, which means D is 2. So if there were a rational map that had this portrait, it would have degree 2. So it would look like this. E of Z over Q of Z, where P and Q are quadratic. Okay, and it would have 1, 2 cycles of period 2. How do you compute a cycle? You set up an equation, you insist that F composed with itself, you look for Z values of Z, for which this is true. If we set that equation up, let's figure out what it would be. This map is quadratic, so when you compose it with itself, you get a degree 4 object, degree 4 rational function. So I can use this notation, R of Z over S of Z. And when I set this equation up, I set this equal to Z, and then I rearrange this, I'm looking for Z values for which this is 0. This equation has what degree in Z? S is degree 4, there's a Z right here, this is degree 5. Included in the solutions of this are the fixed points. That is, solutions that look like this. A rational function of degree 2, you can compute exactly the same way, has 3 fixed points. So in these 5 roots, there are 3 fixed points, which means there are 2 left over. And those 2 together form exactly 1 cycle of period 2. A rational function of degree 2 can have at most 1 cycle of degree 2, not 2. This doesn't exist. Oh, because the local degree here is 2. The local degree, the multiplicity of a critical point is its local degree minus 1. So this doesn't exist. But for you topologists in the room, maybe that doesn't bother you because you can build a map on a topological sphere that has this property. How might you do it? Well, let's just do an example. And maybe topologically is fine. So you could just let's take something that we know and love. Let's take the squaring map. So this is V goes to Z squared. And then I want to build something topological that has this. Okay, so maybe I want to post-compose with a homeomorphism that maybe sends, I need a number that's not 0 or infinity. This is the interactive part. You guys have to give me one. 5, 10, pi, I,
3.
3. 3 wins. Okay, so I'm building a map. It's a homeomorphism from the sphere to the sphere. And under the composition, 0 is going to map with local degree 2 to 3. I'm going to build this homeomorphism. Okay, but that means we should think of this as 0 and this as 3 under this composition. I want 3 to map back to 0. So the squaring map is going to send 3 to 9, and I want 9 under my homeo to go to 0. Okay, so then 0 is going to go to 3 under this composition with local degree 2, and then 3 is going to go back to 0 with local degree 1. So I've just, picking any homeomorphism that does that, and it's very easy to do that, I've just imposed this constraint on this composition I'm building. And now I need another number. Okay, thank you. 1. So under the composition, infinity goes to 1, and I want 1, which under squaring goes to 1. So all you have to do is take the squaring map, post-compose with any, say, orientation preserving homeomorphism on the sphere that maps these points to those points. And the composition has this. But there's no rational map that has that dynamic. This is where things get super exciting. So you could start with, so say your worst enemy comes over for dinner and you just, you're in this sort of chess game with them and they're like, oh, you like to realize portraits. Okay, try this one. This is a good one. This looks terrible. So let's just count degrees again. You can do Riemann-Hurwitz. There's 1, 2, 3, 4, 5, 6 critical points. So 2D minus 2 equals 6. So if there's a rational function of degree 4, sorry, if there's a rational function with this portrait, it has degree 4. Okay, so this doesn't exist as a rational function, and in fact, it doesn't even exist topologically. Even though there's nothing wrong Riemann-Hurwitz wise, and there's nothing wrong local degree wise. This is a completely valid portrait. There is no map from the sphere to the sphere at all with this dynamics. And how do I know that? Well, if you tried to build one, you're going to bump into something that's pretty famous that some of you might have seen before. So I'm just going to extract, the problem is right here. It's with the critical points and how they map to the critical values. So that's the part of the picture I'm going to remember over here. So I have one critical point mapping with local degree 2, another one, local degree 2. And then I have this. And then this is just mapping with local degree 1. So this is how the critical points map to the 3 critical values in that picture. If there were a topological map that had this dynamics, you could give yourself a complex chart to work with, so you could label points. You could call this point 0, this point infinity, and this point 1. And then you could work in local coordinates, and maybe this is A, B, C, and D, S and T. I'm just doing it. At this point, it doesn't quite matter, but yes. So you're going to see there's going to be a problem regardless of how the points are labeled. So if we give ourselves this chart and we write down sort of what an F would look like, these 2 points are zeros. So it would have this in the numerator. These 2 points are poles. It would have this in the denominator. And then there's some scaling factor out in front. Look at this. This is a degree 2 map on the inside, and on the outside, you're squaring. So this is a composition of two quadratics. Any map that has this dynamics, sorry, not dynamics, any map that has this combinatorics, well, just this part, can be written as a composition of an inner quadratic and an outer quadratic, which means you can't have something mapping forward with odd degree. There's a topological argument that doesn't use coordinates that I think is much prettier, but I don't have time to wrap up soon. So there's no topological map that realizes portrait. You try to build one, you will fail. So that means this problem is really hard. How do you know, even if you satisfy Riemann-Hurwitz and you satisfy local degree conditions, you might not even have something topological to work with, forget rational. And this is related to the Hurwitz problem, which Hurwitz stated in the 1890s. And I say unsolved because I should be a little more precise about what I mean. So there's this wonderful paper written in 1984, published in 1984, by Edmonds, Colloquia, and Stong about the realizability of branch data, which is exactly what we were talking about. I was talking about how critical points map to critical values and what their local degrees are. And when you can build a branch cover on the topological two-sphere that realizes a set of data and when you can't. Hurwitz figured out exactly when this works. There's a condition on a symmetric group. You can build covers just like an algebraic topology class. There are constraints, necessary and sufficient condition on what happens as you study called monitoring. You take a base point and walk around points downstairs and study what happens to points in a fiber upstairs. There's some algebraic conditions, but the problem, the Hurwitz problem, is to characterize branch data. Which branch data are realizable? For example, it's still, I believe, open that if D is prime, that it's always realizable, no matter what the branch data is. So we don't know that. So it's hard to check the Hurwitz conditions given this combinatorial shape. So you bump into this problem when you're trying to solve the problem I mentioned. But the good news is, in that paper, they prove, and one can check this sort of by hand, that if your branch data come from polynomials, which means you have one point mapping forward with full degree representing the point at infinity, and all the other data satisfy Riemann-Hurwitz conditions, then that is topologically realizable. So this is great. So if we restrict to polynomials now, then we can always build a topological map that realizes our branch data. So for example, we start with this portrait, we can compute. We have 1, 2, 3, 4 simple critical points, and then one critical point that maps forward with local degree 5. This is polynomial data. This represents the point at infinity for a degree 5 polynomial. Degree 5 polynomial is 4 critical. So what you can do, just like I did before, you can build a topological map that has this dynamics, and that's a step in the right direction. And then the question is there an honest to goodness complex object that is equivalent to the topological one that you can build? And the answer is maybe. And then enter one of the most important theorems in my entire subject by Bill Thurston in the 80s that provides necessary and sufficient conditions under which a topological object is equivalent to a rational as a natural geometry. Okay, but using Thurston's theorem, I did a project with Bill Floyd, Daniel Kim, Walter Perry, and Edgar Sens. And our theorem is, given a polynomial portrait like this one, there is a complex polynomial that realizes it. So all polynomial portraits are realizable. And the way that we prove that is we build an explicit topological model, and then we run it through Thurston's theorem and show that Thurston's theorem applies. And then that gives us those. There are ways to build topological models for this and mess it up So that when you take the topological model that you build, you have a lot of choice in how you build a topological model. When you mess this up enough, run it through Thurston's theorem, the answer is no. Not equivalent. So not all topological models are equivalent to complex ones. Our theorem is there exists a complex one that realizes the portrait, which means there's a way to build a topological one that succeeds when you apply the Thurston theorem. And I think I should probably stop there. I had a whole other half of the time to tell you guys about, but I can do that maybe if anybody's interested later. So I'll stop there. Thank you for listening. Thank you. A lot of people have any questions?
Be a little bit more precise, this model, if you have a topological model, a good one would be actually conjugate, topologically conjugate to.
Yeah, good question. So that's a notion of equivalence that I'll just quickly define up here. This was in Thurston's theorem, the context of the theorem. It's a topological notion. So it's something on the sphere. So if I have, this is the post-critical set, this applies to post-critically finite objects. So I have a sphere with a map, say of degree D, and I've marked the finite post-critical set on it. So that's one of them. And then I have another one. Here. These two objects are equivalent in the sense that I mean on that slide. If there's an orientation preserving homeomorphism B that will send this set to this set, and an orientation preserving homeomorphism psi that will send this set to this set, that are isotopic to each other relative to the post-critical set. So it's a little bit weaker than just homeomorphism conjugacy. Exactly. That's exactly right. So it's you would expect the equivalence to involve some kind of the same notion in domain and codomain, because we're doing a dynamical construction here, but these don't have to be equal on the nose, they just have to be homotopic relative to the mark set here. So that's the notion.
The bad guys, which you cannot realize, you can even homotop them, as long as you homotop relative to the classical set, you're not going to get.
Exactly, you won't get any rational representative. And there are ways. So for example, this guy here is one of those objects. So you take any map like the one we built, for example, and I built it. There's a lot of freedom in the construction I did. It was up to like I only chose 4 points where they went. So in the construction, so we showed that there are lots of maps that realize this portrait, but we know just from counting degrees that this can't be realized by a rational function, which means any topological representative that you build cannot be equivalent to a rational map of degree 2, and these are called obstructed maps. And what happens is Thurston's theorem is this amazing statement that has a criterion. You take the topological map that you build and you run it through this procedure, and Bill provides necessary and sufficient conditions that you can check in favorable cases. So it's a condition on checking how curves map on the sphere under this particular map that you built. And if this is not equivalent to a rational function, then there's a topological obstruction. And he tells you exactly what that will look like. The problem is it involves an infinite search, which is why any successful application of the theorem is kind of a big deal. More questions? Well, if you guys don't have any more questions, I just wanted to tell you about one thing that I think is cool, especially for those who know about Belly's theorem, and then I'll stop. So the other question I was asking about post-critical sets, turns out any finite algebraic subset of the Riemann sphere that contains at least 2 points is the post-critical set of something, which is kind of cool. So that's a project I did with Kurt McMullen and Laura DeMarco. So we understand that if you ask me which ones arise for degree 53 maps, I don't know.